Hello guys, this presentation or problems will cover several topics in physics and there is no particular order to it. Hope you will learn something as you try to answer them on your own. Which phenomenon in modern physics can be explained by wave-particle duality? Letter A, quantum entanglement. Letter B, photoelectric effect. Letter C, special relativity. And letter D, Doppler effect. The answer is photoelectric effect is the emission of electrons when light or electromagnetic radiation hits a material. We typically view light as waves, but photoelectric effect shows the particle-like behavior of light. Here we have a simulation for photoelectric effect. We have conducting plates like that of capacitors where light is shown. The charges are ejected from the surface and these charges are electrons. This shows that light collides with the surface, ejecting the particles from the surface. In which of the following processes is no heat exchanged with the surroundings? Letter A, adiabatic. Letter B, isothermal. Letter C, isobaric. And letter D, isochoric. The answer is here we have the isochoric process as highlighted by the red arrow. We see that there is a drop in its temperature as it drops in pressure at constant volume from its initial position A with initial temperature Ta. Isochoric process is where the volume remains constant as indicated by the pressure versus volume diagram. Here we have the pressure-volume diagram for an isobaric process. We see that there is an increase in temperature as it moves to a larger volume at this position. In this process the pressure is constant as shown in the pressure versus volume diagram. Here we have the pressure-volume diagram for an isothermal process. We see that as it decreases in pressure and increases in volume the temperature remains the same at this new position. An example for this type of process is the melting of ice. At this position with temperature T3 is equal to Ta. Here we have the pressure-volume diagram for an adiabatic process where there is no heat gained or lost by the system. We see that as it decreases in pressure and increases in volume the temperature T2 at this new position is less than Ta. In this thermodynamic process, there is no transfer of heat into or out of the system. In other words, during an adiabatic process, the system is thermally isolated, and any change in internal energy is solely due to work done on or by the system. So, the answer to the problem is an adiabatic process. Which of the following is not a fundamental particle in the standard model of particle physics? Letter A, neutrino. Letter B, quark. Letter C, graviton. And letter D, lepton. The answer is here we have the particles in the standard model of particle physics and we see that graviton is absent. The primary reason why the graviton is not part of the standard model is that the model does not incorporate the gravitational force. Gravity is described by Albert Einstein's general theory of relativity, which is a classical theory of gravity based on the curvature of space-time caused by mass and energy. The standard model, on the other hand, is a quantum field theory that successfully describes the other fundamental forces but does not include gravity. The first law of thermodynamics is also known as the law of letter A, conservation of mass. Letter B, conservation of energy. Letter C, conservation of momentum. And letter D, conservation of charge. The answer is the first law of thermodynamics can be stated as, the total energy in a system remains constant, although it may be converted from one form to another. It is a form of conservation of energy. For example, when we eat food we convert it to a form of work, heat, or store it in our bodies and use it later. Or when the energy from the sun the plants can use it for growth and production. The plant can then be consumed by other animals and so on. Basically, the energy from one type of media is just converted from one form to the other and the total energy of the system remains constant. This is the first law of thermodynamics. Mathematical expression of the first law of thermodynamics is shown here in equation 1. Where delta U is the change in internal energy, Q is heat, and W is work done or on the system. Internal energy refers to the kinetic energy of the particles inside a chamber. Heat Q is introduced to the system where it contains an ideal gas. This expands the volume of the gas, pushing the piston upward with work W. The internal energy U changes from state 1 to state 2 and it is expressed as equation 1. The internal energy is the sum of the kinetic energy and potential energy of the particles, which is the same as conservation of mechanical energy. In a wave equation, what does the wave vector k represent? Letter A, frequency of the wave. Letter B, wavelength of the wave. Letter C, speed of light in a vacuum. And letter D, direction of wave propagation. The answer is. Here we have a wave equation as shown with its plotted figure. The wave on the string travels in the positive x direction with a constant velocity v, and moves a distance v times t in a time t. The wave number k as a wave vector contains information about the direction of the wave and its spatial frequency. It has both magnitude and direction. The magnitude of the wave vector is related to the wave number, which is the spatial frequency of the wave. The direction of k indicates the propagation direction of the wave. Which of the following statements is true about the second law of thermodynamics? Letter A, energy cannot be created or destroyed. Letter B, heat always flows from a colder body to a hotter body. Letter C, entropy of an isolated system never decreases. And letter D, pressure and volume are inversely proportional. The answer is. The second law, in its most general form, states that the entropy or disorder of an isolated system tends to increase over time, or at least remains constant in processes that are reversible. The concept of entropy is closely tied to the idea of disorder or randomness in a system. In simple terms, as time progresses, systems tend to evolve toward states with higher entropy, reflecting an increase in disorder or randomness. Here we have a simulation of particles being heated and we see as the temperature is increased the particles move in random, creating disorder. So we see that the disorder moves from low to high disorder, which makes that for an isolated system entropy never decreases. In this case we also see that pressure and volume are inversely proportional to each other. In the context of the theory of relativity, who formulated the theory of special relativity? Letter A, Isaac Newton. Letter B, Albert Einstein. Letter C, Max Planck. And letter D, Erwin Schrödinger. The answer is. Albert Einstein made numerous groundbreaking contributions to physics, fundamentally reshaping our understanding of the physical world. One of those contributions is the special theory of relativity. In 1905, Einstein's paper on the special theory of relativity revolutionized our understanding of space, time, and energy. It introduced the famous equation, expressing the equivalence of mass and energy. In this theory, the laws of physics are the same for everyone, no matter how they are moving, as long as they are not accelerating. Key concepts are time dilation. Time can move slower or faster depending on how fast you are moving relative to something else. Second is the length contraction. Objects can appear shorter in the direction of motion when moving at very high speeds. And third is the mass-energy equivalence. E equals mc squared, which means energy and mass are interchangeable. Which of the following is not a state function? Letter A, temperature. Letter B, pressure. Letter C, work. And letter D, internal energy. The answer is in thermodynamics and physics, a state function, also known as a state variable, is a property of a system that depends only on its current state and not on the path it took to reach that state. In other words, the value of a state function is determined solely by the current condition or state of the system, and it is independent of the process or history by which the system reached that state. Work is not a state function because it depends not only on the initial and final states of a system but also on the path or process taken between those states. This is shown in the equation. Work is associated with the transfer of energy and is influenced by the specific details of how the system changes from one state to another. In classical electrodynamics, what does Lenz's law describe? Letter A, the relationship between the dielectric constant and the electric field strength. Letter B, the behavior of magnetic materials in the presence of an external magnetic field. Letter C, the direction of the induced current in a closed loop due to a changing magnetic field. And letter D, the behavior of charged particles in an electric field. The answer is Faraday's law states that the induced EMF in a closed loop equals the negative of the time rate of change of magnetic flux through the loop. The negative term indicates that it opposes the external magnetic field as a consequence of conservation of energy. Another way of stating this is by Lenz's law, which states that the direction of any magnetic induction effect is such as to oppose the cause of the effect. A square conducting loop moves across a magnetic field which is going out of the page. And we determine the direction of the induced current, which will produce an internal magnetic field that will oppose the rate of change of magnetic flux or oppose the magnetic effect. When the closed loop enters into the magnetic field, there is an increase in magnetic flux. The external magnetic field pointed out of the page, then the internal magnetic flux must be going into the page to oppose the magnetic effect. So the direction of the internal magnetic field must go inward on the right side and out of the page on the left side of the wire. Using the right-hand rule, the direction of the induced current must be pointing upward in this segment. The induced magnetic field is moving clockwise to create a magnetic field that will counter the magnetic flux of the external magnetic field. Looking at a different view, we see the internal magnetic field points in the direction opposite to the magnetic field in order to oppose the magnetic effect. When the loop leaves the magnetic field, there is a decrease in the magnetic flux, and in order to oppose this effect, the direction of the current must be oriented in order to increase the magnetic field. Using the right-hand rule, the direction of the induced current must be pointing upward in this segment. In this case, we determine the direction of induced current when the area of the conductor in the presence of a constant magnetic field is decreased. The magnetic flux is reduced suddenly, so there is a decrease in magnetic flux, which means that we must add the internal magnetic field to oppose this effect. The entropy of a system is a measure of letter A, the internal energy of the system. Letter B, the disorder or randomness of the system. Letter C, the temperature of the system. And letter D, the pressure of the system. The answer is entropy is the study of disorder of the system, as shown here by the disorder from solid to liquid. The end for now. For questions and comments, you may send them to diyslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Thank you for watching and see you in Part D.